Today we define orthonormal lists and orthonormal bases. Finally, a basis that does not turn coordinates into paperwork. A basis is already useful. An orthonormal basis is a basis with manners, unit length, and no unnecessary leaning into each other. Start with a list of vectors in an inner product space, not a set. A list order still matters, because apparently even vectors need seating charts. The normal part means every vector in the list has length 1. The orthogonal part means different vectors in the list have inner product 0. Together, both conditions say that the inner product of Ej with Ek is the Kronecker delta. 1 on the diagonal, 0 off the diagonal. Very tidy. Suspiciously tidy. The point of orthonormal lists is that cross terms disappear. The algebra finally cleans up after itself. If X is a linear combination of an orthonormal list, its squared length is just the sum of the squared absolute values of the coefficients. This is why orthonormal lists are so convenient. The coefficients do not interfere with each other, which is more than we can say for most systems humans design. An orthonormal basis is an orthonormal list that is also a basis. The definition is short because the burden was outsourced to previous definitions. So an orthonormal basis gives enough vectors to represent every v in V. And the vectors are mutually orthogonal unit vectors. With an orthonormal basis, coordinates are extracted by inner products. No solving a system every time. A small mercy in a universe of notation. Now the standard example. In Fn, use the standard inner product and the standard basis. In the plane, these are the two coordinate arrows. In higher dimensions, the same idea continues, even though our eyes quit after 3 dimensions like cowards. Each standard basis vector has length 1, and different standard basis vectors have inner product 0. Therefore the standard basis is orthonormal. And because these vectors also span Fn, they form an orthonormal basis, not merely an orthonormal list. The next question is obvious. If we start with an arbitrary basis, can we manufacture an orthonormal basis from it? Yes, naturally. There is an algorithm. The Gram-Schmidt process keeps the same growing spans, but cleans the vectors one by one until they are perpendicular in length 1. Next time, we subtract projections, normalize, and repeat. Vector laundry, but with better notation. An orthonormal list means unit length and mutual orthogonality. An orthonormal basis is just an orthonormal list that also spans the whole space. The standard basis is the easiest example. Next, Gram-Schmidt shows how to build orthonormal bases when the universe hands us an ugly basis instead.